Felix Li. It's odd introducing him since I'm a co-author on this paper. It means I can ask intelligent questions at least, I hope. So this is I haven't been here so much that we're actually taping in the front. So for those of you who are students, this is great. I would recommend to all the students that they present once, watch them, and then get it taped and watch yourself. It is a terrifying experience to watch yourself give a talk. Because all those ums and likes and awkward sentences, when you watch yourself, it's terrifying. But it's absolutely the best way to learn to give a public presentation. So I would encourage all the PhD students here, twice before you go on the job market, to give a talk where it's taped and then watch yourself. And so since Felix is hitting the job market in the near term, it's time for him to suffer the torture of having to have himself taped giving a talk. And today he's talking about generalized method of moments and using it to combine population and survey data. So I'll just give you the 2-second summary from my point of view. This is a new or different way of thinking about how we do weights in the small surveys that many of us do on a regular basis, or in principle even in the large surveys that big organizations like Statistics Canada might do. So this is in some sense a new, more efficient way of dealing with those issues. So I'll ask the question, how many of you here in your research have ever done a survey? Okay, so how many of you in your research, when you've done a survey, have weighted the survey so that it's representative of the population you're surveying? All right. So that's the issue that we're thinking about here.
All right. Thanks everyone for attending this talk. Again, this is a joint work with Professor Sweetman and Professor McGee. It's about using the generalized method of moment to combine the population and the survey data. Here's a framework. I'll briefly introduce the motivation, move to the presentation of the estimator, and spend a fair bit amount of time in the Monte Carlo simulation study the property of this estimator, and then move to a small application using the midwife data, and then draw a conclusion. All right. I think everyone heard this story before. This is a blind man with an elephant. They were trying to, because they cannot see the elephant, they were trying to describe what the elephant looks like. However, because the elephant is big and they touch the body of the elephant, some touch the trunk and say, okay, this is like a snake. Some touch the leg and say, okay, this is like a tree. However, they don't know the elephant looks like this. We are like the blind people, because we, as a researcher, we have only access the survey data might not be representative for the whole population. So the inference that we draw from the survey data may be biased because we only touch one part of the big elephant. All right. So this gives you a general idea what the topic is about. Is they share some analogy with the technique. So again, a survey is usually considered as an instrument to draw some inference for a big population with only some observations in the population data. One way to motivate this technique or this paper is that in most of the cases in health services and health economics, there are lots of surveys, especially those in the epidemiology, in the clinical trials. This type of survey data frequently suffer from non-response or attrition issue. So it's not representative for really the target population that we're trying to look at. And usually the researchers just run regressions or describe some statistics based on the survey data by itself. But obviously this is a wrong thing to do. So an alternative way to do this is to reweight the data. So that's to introduce the Surveywait. Building on the idea of the Surveywait, this technique kind of simultaneously estimate the parameters that we are interested in. at the same time reweight the distribution by forcing the moment conditions between the population and the survey to be equal. This is based on the Halstein and Imbens and McMaster's paper. The technique at that time was advanced and quite difficult to implement because they need very complex programming. But now this data can allow us to perform it quite easily, and there are some limitations for this methodology, and that's we have to assume the missing at random assumption based on the observables, and also for lots of the economists who do reduced form estimation, one critical issue is that the right-hand side variable here have endogeneity issue. This technique is not trying to solve any endogeneity issue. So this is the kind of limitation of this technique. And again, when we were trying to draw some inference from the target population, we have this population on the left, we have the survey on the right, and during this process, there are lots of things that can make the survey data not representative. For instance, the first step might involve the survey design, and you may decide, okay, what's the survey rate, what's the sample size, and maybe stratify your sample based on the region, based on your age, sex, for instance. So there are stratifications based on the endogenous variable or exogenous variable, and then you get your target sample. And based on your capability to allocate these people, some of the people may be successfully contacted, and they may refuse to reply. So there's non-response issue here, and then finally the survey sample might be the distribution of the survey sample might be quite different from the one that you are really looking for. So using this technique can be applied when you are doing your own survey using an administrative framework. And so at one hand, you may access to the administrative data or some census data. It may be an individual data with fewer number of variables, and maybe you only have some marginal information at a macro level. For instance, the expenditure for mail in Hamilton, for instance, might be just one number, might be several numbers at the aggregate level, but we can use this information to draw better inference of the target population. Oh, again, lots of the researchers maybe in this room know that, okay, there is administrative data, whether I can link this administrative data to the survey data. First of all, even we have the individual administrative data, because of the confidentiality, somehow we may not be able to link. In this case, it's not necessary that we need to link. We need the information only, not necessarily link whatever the information there in the administrative data to the individual that appear in the survey. Okay. Here are some literature from the statistics. Again, there are lots of other literature from the economics, like Imbens have a series of papers on the endogeneity. Sorry, not the contaminated data or endogenous stratified data. Those are all related, but on the other hand, in the statistic literature, there are also the way to solve this problem by using the auxiliary information to weight the survey data to make it more representative. The popular one was from a seminal paper by Holt and Smith using the post stratification. And later on, there are more methods developed, such as linear weighting and other weighting schemes. However, because of time, I don't have time to discuss these in detail, but there are certainly some drawbacks of this method. For instance, post-stratification suffer from empty strata. If you specify your strata in quite detailed strata, you may have 0 observations in your sample, so that you cannot really weight it. Also, compared with the current technique that I'm going to introduce, this one needs more observations, like the observation number in each strata, but in this case, it's not necessary. So we have some advantage by using this technique. I realized that maybe some of the audience may not have adequate background of econometrics, so I may spend 1 minute on this method of moment, or generalize the method of moment, so that you may not be confused for the next slide. And this a moment function can be any form. For instance, the easy example is the mean estimation. We always estimate the mean of the expenditure, for instance, the health expenditure, for instance. And the moment function is fairly simple. It's the expenditure minus the mean. And we know the population moment, if we know really the target population, we know that the expected value of the difference between the individual expenditure and the average, the mean of the expenditure, the expected value equal to 0. However, we don't have the population data, we only have the survey data. So what we are trying to do is to use whatever the observation that we have and get the mean of the expenditure. All right, this is I think the easiest example that I can think on top of my head. Commonly, we use the OLS. You can familiar with this, the ordinary least square, and this is we make assumption that conditional on the observables, the expected value of the error term equal to 0. So this is the popular orthogonal condition that the x times whatever you have in the residual, the error term, they time to each other equal to 0. So the population moment will be the expected value of this moment function equal to 0. And what we have is to use the survey data, and we know that when the beta appear at the true value, or the expected value of this moment function is 0. And there's a typo here. There should be x prime times beta here.
Felix, just a really quick question,
Sure.
make sure I'm not totally off. So is the sample moment condition a measure of variance then?
Not necessarily variance. It can measure the mean. It can measure the variance. It can you can measure. I mean, if you are trying to estimate the partial effect or the parameter slope coefficient, it can be a function of the parameter. And in this case, you are trying to estimate the partial effect, like whether male, for instance, have more likely to spend more in healthcare expenditure, for instance. So it can be variance, can be mean, can be other thing, right? Yep. Right. So I'll move to the presentation of the estimator, and this is the core of the methodology. This is from the Halstein and Invens, and I slightly changed the format. There were two types of moment conditions in this framework. The first type is again back to this, the OLS, the ordinary least square, is the orthogonal condition, is the OLS moment, plus there's a weight in the denominator, so it's a Lagrange weight, because there are some parameters that we need to estimate here to reweight. Again, the second type of the moment conditions is that the moment that I get from the population, for instance, the average expenditure, health expenditure for female, for instance, I have this information. I force the moment of the sample equal to the population and weight it as well. So these match the population and the survey, the sample moments. And there are two type of parameters that I need to estimate. This is the model coefficients and these Lagrange multipliers. And so we know that in this framework, the first type of moment conditions, the number of the moment conditions equal to the number of axes, and the number of the moment conditions equals to whatever the information I have. So in this case, the number of the estimators that I need to estimate equals to the total number of the moment conditions. And this is, in fact, a just identified case. It's not a generalized method of moments. Sorry, Major?
Initially, then I'll ask my question.
Sure. Sorry, back to this. The generalized method of moments is that when you have more moment conditions than the number of the estimate, the parameters that you try to estimate, this is generalized method moments. If you really want to think it in an easier way, you can think that you have two equations and two unknowns, and you will have these two unknowns solved perfectly. However, if you have three equations and two unknowns, there's actual information that you add. How can you estimate it? Then Peter Hansen, who was recently announced as a Nobel Prize winner, he had created this generalized method of moments in the 1982 a paper in Econometrica about this. Basically, I don't want to spend too much time on this, but it's trying to minimize kind of a norm of the average from the survey moment conditions, and this is just I just identified case. We use the GMM or generalized method of moments because Imbens and Hallestein use this terminology, and we know that method of moments is just a special case of generalized method of moment. Right? Okay, back to where we had. After we estimate these, we can simultaneously generate the weight for each observation, and after matching these population and sample conditions, we will achieve that the weighted average of the age will be equal to the mean of the age from the population data. That's our goal. And this framework is like to solve a Lagrange equation subject to these actual moment conditions or this marginal information and effectively reweight the sample. We know that this technique from Hallestein and Imbens have desirable asymptotic properties. However, we don't really know its performance when we in reality have a smaller amount of observations in the data. So we spend a fair bit amount of time on these Monte Carlo simulation study. And basically the idea is quite simple. We follow the data generating process as y equals to a dummy equation involved with a dummy variable and a continuous variable and an error term. And the continuous variable and the error term follow the normally distributed 0, 1. And I will generate a big population data and sample it with so many times and run the regression, store the regression result and compare the distribution of the estimate from so many replications. That's the Monte Carlo simulation. And I will take a look at two general cases. One is that there is correlation between the dummy variable and continuous variable. One is no correlation. And after I generate these population data, this is fairly a big number. I assume there's fewer sampling errors when I set the population to have 100,000 observations with 500 observations in the sample as a baseline. And I will draw these 500 observations from the population data based on these 8 sampling schemes. And you can see that I highlighted the one more interesting one that I will show you more in the future slides. The first is the simple random sample, which has the same probability for each observation drawn from the population, and sample on the endogenous variable that you are trying to estimate, you are interested in. And I will set a threshold, which is in this case the median value of y. For those y smaller than the median, I have a smaller probability for that observation to be drawn, and a higher probability for those y larger than the median y to be drawn. In this case, I set this to 100 and this to 400 to make it 500. And you get the idea. The rest of it follows the similar idea. The last one is more complicated. The sampling scheme involves all the variables. And these are the regression results regressions that I will compare. Of course, I will compare the OLS. That's what most researchers was trying to do without relating. And then you can see these 5 GMMs. The first one that I use the information only from the dependent variables, which is the mean of the dummy variable from the population, the mean of the continuous variable from the population data, and the mean of the y variable that I draw from the population data. The second GMM use the information both from the dummy variable and the explained variable. GMM3, we assume we don't have any information from the dummy variable. However, we have the information from the continuous variable and y. The last two are more comprehensive, which have a mixture of the dependent variable and the independent variable. And we don't think these two cases are interesting, because if we have all the information that we have, why do we have survey data? So more realistically, we're gonna take more look at this OLS with this GMM1 to GMM3 and compare the results from there. Okay, these 4 charts are the probability density function of the estimates from 1,000 replications. That means I draw 1,000 samples and run regressions and store the estimate and plot the estimate from that 1,000 observations. And I compare the estimate from the OLS and the estimate from GMM1 to 3 and plot this curve on this graph. And you will see that the both curves from the OLS and use that as a benchmark. And we can see that since this is simple random sample, we know that the estimate from the OLS will be unbiased, and it is true because it peaked on this true value of 0.5, same here, and for the continuous, the parameter from the continuous variable is negative 0.5, which is the value that I set. The efficiency gain is clearly from the variance deduction in this case, because when the sample is simple random, the estimate will be unbiased for both OLS and the GMMs. And another interesting thing that we observe is GMM2, which has more information on the dummy variable. We see that this green line, the green dot line, is really concentrated than the rest of the models on the true value, which shows that the more information that you have from the variable, the more precise of the parameter of that variable that you will estimate from this GMM framework. We can see that when there's no correlation, and when there's a correlation, the pattern looks similar. And this is a more interesting case that I would like to present. When the sample is based on Y only, this is a pure endogenous stratified sample. As what we expect, the OLS is biased, and we can see that in this case, the GMM1 is also biased, but we can see that there is efficiency gain from the GMM2 and 3 is that there is some bias deduction or bias correction from the OLS. And again, the more information that you have for the dummy variable, the more precise of the estimate. Similar pattern for the correlated cases as the uncorrelated case. And from the previous case and this case, we all observe that the efficiency gain from this GMM1 by using the information only from the dependent variable may not large. This is a slightly efficiency gain, and in this case is almost on top of these OLS, is almost the same as the OLS. We feel confident to say that it's necessary to have the information of the variable that you are interested in the GMM framework. Yes.
Are the OLS using any weights in this?
No.
So that's why they're so biased.
Right.
Would they be unbiased if you use sampling weights?
The sampling weights from what?
Well, I mean, you could use inverse. Like if you knew, you just said you sampled on Y, right? So you know what percentage of those above and below of the population, so you could put some sort of
Sure, like the
inverse propensity.
post stratification strategy, like you give more weights for those who have lower probability to join.
Yeah.
We haven't done the comparison for that, but you know, the idea is that for health services or health economics, sometimes people do not know any information about the population. Rather
Okay, so we're assuming that we don't know the weight.
Right. So, and compare to someone who do the OIS regression without considering any weight, this technique work much better, I should say. Yes. But yeah, in the future, it's a good point. I'll compare the OLS with the other technique and compare with this technique and see how it goes. Again, as a robustness check, I set population to be very small, like 500 observations, so that there are more sampling errors. And I set the survey data as the sample size is half of the population, and we see the similar pattern as these cases. So it's very robust, and we extended the model by 3 dimensions. Actually, this is another dimension, but these 3 are the core extended, and we changed the sample size because the baseline is 500 observations, but we don't know whether we vary the sample size to very small and very large. Also, we are not sure about the explanatory power of the dependent variable, whether we change the explanatory power, whether the model perform good or bad. How about if the error term has a heteroscedasticity? When we introduce the heteroscedasticity and change the amount of the heteroscedasticity and see the property of the estimator. And then, in reality, we may have lots of explanatory variable on the right hand. And in this case, we extended the model to include more dependent variables and see by adding some information from only a couple of dependent variables, whether that can change the estimate for the rest. Here is the result from changing the sample size, and you can see that the result from whether I change the sample from very small 150 to a sample with 5,000 observations. And here I show the simple random sample with correlation, without correlation, sample on the dependent variable, sample on all the variables, like the most realistic case, I assume. And we can see the entry of each box is a ratio of the mean squared error from the GMM with the mean squared error from the ORS. The mean squared error shows not only consider the biasness but also kind of the variance. So it's the larger the mean squared error of the model is, the worse performance of the model. So the ratio actually can show the relative performance of your GMM compared with the ORS. And if the ratio is larger than 1, that means the GMM perform worse than the ORS. And when the ratio is smaller than 1, it's better. And the smaller, the better. We can see that the results are not very sensitive to the sample size. And we see the same pattern that GMM 4 and 5 generally perform better than GMM 2 and 3 because it has more information there. And again, we see GMM 1, for some of the cases perform better, but for other cases perform worse. And to make the picture more clearer, we show the probability density function. Again, this is sample on Y. I show this case because I want to show the bias correction. And we see that when sample goes from 150 to 5,000, this is the relative performance between the ORS and the GMM. And you can see that there is certainly lots of efficiency gain in terms of the bias correction in these cases. Again, the second extension is that I changed the variance of the error term in my DGP so that the R square in this case varies from a small to large. And we see that when I change the explanatory power of the independent variable, the result again is not sensitive to what value of the standard error I set there. Is relatively robust. Again, this is the PDF. You will see the efficiency gain from these cases. This is more interesting, I assume. When we introduce heteroscedasticity, here are the heteroscedasticity is the variance of the error term. I use these as a variable of the continuous variable in my case, and the tau or t shows the amount of the heteroscedasticity, and when tau equal to 3 it shows, and when tau equal to 3.8 shows relatively small amount of heteroscedasticity, where tau equal to 3 is fairly big amount of heteroscedasticity, and we see that this technique performed really good in the situation that there are large amount of heteroscedasticity introduced in this framework, and we can see the ratio dropped really to 0.001 in this case. It's fairly robust, and we can see that basically when we introduce a large amount of heteroscedasticity, the performance of OLS was really bad. And by showing these figures, we can say, or from this PDF, we can say that the GMM, by including the marginal information, will return a relatively stable estimate when the heteroscedasticity was introduced. Alright, and then we want to further extend the model to make it more realistic, that we again have information from two variables in the model. We want to extend the case that there is an actual variable that we don't have any information from the population data, and there are 4 survey-only variables, and then there are 10 survey-only variables that we don't have any information access. And then I assume all the variables are correlated, set the population and survey observations is this, and I'll show you the results on sampling on Y. It's quite interesting that, as expected, because it's purely endogenous stratified, the parameters from the first 2 variables, the estimate is unbiased, as what we expected. However, even though we have no information about the 3rd variable, we can see there's efficiency gain from these informations, and the efficiency was from the bias correction for the last variable that we don't even have the information about. Same thing when we extend it to 4 survey-only variables, and they all become relatively unbiased. And when we extend it to have 10 survey-only variables, again, the estimate is really concentrated on the mean. And another interesting story that we can see from these 3 graphs is that the relative performance between the GMM 3, 4, 5, and 2 is not dramatically different, especially in these cases. And see, and the message that I want to deliver here is that if they are correlated, by using the information from one variable, can really give you a better estimate for the other variable without using the information from that variable. So it's not necessary for us to know all the information about these variables. As long as we have one from the dummy variable or the continuous variable, the performance is already much better. Alright, I've spent a lot of time on the cases that there is that this technique perform very nicely. However, there are cases that the technique may fail. This is a case that when we have fewer observations to match. For instance, I just illustrate this as an example that I sample on the continuous variable. And again, the threshold, because it's a continuous variable, normally distributed at 0, 1. So the benchmark is set at the mean 0. For those less than 0, I randomly draw 550, 550, 100, 400, 50, 450, 10, and 490. So you can see that from this region, I sample less and less observations, almost no observations. And in this region, I randomly draw a large proportion of the observations. And you will see this case is actually equivalent to simple random sample. And this is the baseline model. And these are the new columns and new results. When we see that there are really very few observations in this region, when x is smaller than 0, some cases like GNN3, in this case GNN1, 2, 3, all kind of perform worse than the OLS. So we have to be careful about the information about how biased the sample is. Sometimes if there's basically no observation, for instance, an extreme example is that in your population you have both male and female. In your survey, only the female answered and no male answered. So that's kind of extreme case that introduce this actual information from that gender may not work quite well. Okay, let's move to a small application about midwifery program. It is a joint program from 3 universities, Laurentian, Ryerson, McMaster, and it was initiated by the Ontario Ministry of Education because the lack of the midwife in Ontario. This program had a very large dropout rate. And the research question that we are trying to ask is why there are so many people drop out in this program and how to prevent it. And there was a survey conducted to the students in Ryerson and McMaster University, asking them about their background information, about the class experience, the study habits, the challenge that they experience in the program. The survey participants includes the grads and the dropouts. At the same time, we have access to the administrative data, but with only quite limited information. We have age, we have the year of admission. It's like a Excel spreadsheet, but because of the confidentiality, we cannot really link. We don't know who is who. We know where the university they graduated or they still in. And this survey data is a biased data for sure. Why is that? Because it's a pure example of the endogenous stratified. Because these two group of people, the grads and dropouts, are surveyed from a very different channel. Those grads were sent by email by the Association of Ontario Association of Midwifery. So for those who practice, majority of them grads perform practice as a midwife. So it's very unlikely they didn't receive the email. So they are easily to be located. However, for those grads, a mail was sent by the address that was last known, and they may move, they may go somewhere else, and in order to connect more of them, other method was used like Facebook or Google, friend, whoever knows the contact of this person. So they really, like the variable that we are interested in was contacted through different channel, and we observe that the sample over the population between these groups are different from each other. And we know the capability of allocate the grads and dropout are very different. So there is a substantial non-response. And the model that we are trying to estimate is a fairly simple linear probability model with the variable whether dropout or not as the dependent variable, and independent variable depend on a dummy variable for those who got admitted between the year 1996 to 2000. The reason why I make these people group together is that from the observation, I saw that the program got expanded and the number of recruitments got larger starting from the year 2001. So I think, okay, this is, they might share some policy change or that. So it's natural to group these as a dummy variable. And the McMaster dummy, age, and other variables. The other variables include the person's background information, whether they're visible minority, whether they have children, whether they, also it includes the class experience, difficulty that they experienced during the program, and at the same time, again, we access to the administrative data. And the target is that we want to use the Imbens and Hellerstein's generalized method of moments technique to reweight these data, survey data, to make the microeconometric estimation more unbiased, more approach to the target population, which means everybody in these administrative data. All right, and there's a snapshot of the some summary statistics of the dropout between the survey and administrative data. We can see that Ryerson and McMaster looks more representative, I should say. However, the Ryerson, you will see that the mean of dropout in this year of admission different from the administrative data, and in this year of admission quite different from this. And there are three GMM models that we want to construct. The first, again, we really want to use all the information that we can from the administrative data. The dropout, which is the mean of the dropout, the mean of the dummy variable, which is the percentage of the people from who got recruited between the year 1996 to 2000, the percentage of the McMaster student, and the mean age. The second of GMM is that we do not only use the mean of these variables, but also some interaction between the dropout and the dependent variables. GMM3, not only building on GMM2, adding the interaction term between the dependent variables, which is this dummy variable, McMaster dummy variable, and age. The reason why I want to compare these three is as a robustness check whether the result by using this technique is really sensitive to the information that I use. If the results from GMM 1, 2, 3 are dramatically different from each other, then we are in trouble. This technique is not, is very volatile. However, this is the result. There are two specifications. First column, big column 1, I only introduce this year of admission dummy, McMaster dummy, age, and some other information like visible minority, whether they require to get autobiography before admission, and whether she had children under 5 before admission. This is some information that these two specifications are trying to answer different policy questions, and this is some information that we know before they got admitted, and we know how to prevent and kind of screen out what type of people who are likely to drop out. And this is kind of more variables that included for those experienced during the program. Here I'm not trying to argue whether the model is really correctly specified, because for sure there are lots of endogenous variable included, which is highly correlated with these variables, because it used to be quite significant, become less significant. That's the nature of the data. I'm here not saying this is the right, correct model. However, I'm trying to show the two things. The first is we do see that the OLS result, they're basically, by using the survey data, we cannot draw any conclusion about the correlation between the different variable and whether they drop out. However, the GMM 1, 2, 3 all show that if you're from McMaster University, you are less likely to drop out, which is kind of, we also see from the comparison between the administrative data and the survey data, and these can capture that. However, the survey may be from lots of dropout from Ryerson University. They refuse to answer the survey, so they are less representative, for instance. And we also see that if you are a visible minority, you are less likely to drop. And if you are required by providing an autobiography before you got recruited, I don't know what information this decision was based on, but somehow this sending a signal that these people may have some disadvantage completing this program. So this is very powerful variable. However, the OLS didn't succeed capturing. However, the GMM showed that when they require these additional documents to support their application, they are likely to drop out. And here, I wouldn't really spend too much time to argue whether the tutor issue really make you to drop out, or the health issue is really not important. But we do see that the result from the GMM 1 to 3, the magnitude of the estimate and the significant level are quite similar. So it's not sensitive what information or what combination of the information that I include. The estimates are very stable. And I realize the time, so I have to hurry. This is the lambda coefficients. There are two types of coefficients: it's beta and Lagrange multiplier. And this is those lambdas. And the null hypothesis is that all these lambdas are 0, and the chi-square test is very significant. It's significant as 1%, which is strongly reject the null hypothesis that these lambdas are all 0. In other words, it is strongly reject the null hypothesis that the survey distribution and the population distribution are identical. They are not. And to make it more clear, I show the cumulative density function of age that I plot from the survey data and administrative data and the weighted administrative data. Clearly we see this line shows the survey data, and we see on average the younger people are overrepresented, whereas from the administrative data show that the average age is larger. However, after I use the weight that I constructed by this GMM framework and use the weighted cumulative density function, we see that this weighted survey data and the mean data are quite next to each other, quite close to each other. So it shifts the distribution, make it more representative as the population. Alright, I'll draw a quick conclusion. We all know that the survey data suffer from non-response and small sample size and attrition. At the same time, administrative data provide some senses. And this paper used the Halstein and Inman's technique with the generalized method of moments by adding the actual information and simultaneously reweight the data and provide the estimate in the microeconometric framework. And then we spent a fair bit of time on the Monte Carlo simulation study and show that these approach really have a appreciable reduction in both bias and variance. And we use a midwife as an application to show this technique can be applied in the health human resources context and can be widely used in general in health economics and health services. All right, thanks very much. Is there any questions and comments and clarifications? Yes?
So well, the first question I was going to ask was, because you're forcing the moment to population, right?
Yes.
Is there an inherent bias to, or is there an inherent trade-off between like whether the GMM tends to reduce efficiency or bias more or variance more? But I guess no, based on the graphs, it really depends on the context. Is there like a trade-off between variability versus unbiased variance, reducing variance?
I think in terms of trade-off, yes. If you include, I mean, if you treat that macro moment as truth, and if you the information that you have is really the target population, and you want to move your survey distribution towards the target population, then including that information, for sure there's efficiency gain. However, if you include more information which is redundant, there is some degree of freedom reduction, and then there's trade-off whether you include too many redundant informations and get some large variance in that case.
Okay, so the other question I was going to ask is, so you showed that you don't need a lot of information to get good estimates from the GMM estimator, right?
Yes.
Based on your Monte Carlo simulation, do you think you're in a position to state which estimator to use when?
Oh, this is very difficult. The reason why the graph that I showed you was that when these variables are correlated, I think it's very powerful to use the information that you're interested in. For instance, the dropout as my applicant. In my Monte Carlo study, I use the information on the explained variable y. Using that really is powerful, and using the information from the axis that are correlated with other axes that you don't have information, which also are powerful. However, what information you are trying to use, depending on what information you have at this first time, and also it's a judgment call whether you think it is relevant to the sample selection. So again, back to the original assumption, this is based on missing at random, conditional on the observable. If the selection is something that we have no information about, unobserved, then no matter what information you include, it fails. Yeah. So
Any time for one more before we break?
Yes. If not, well.
Interesting applications.
Yeah, there's another interesting application that I'm currently working on optometry. I'm trying to show another model. This is based on the orthogonal condition from OLS. However, this technique not only work for OLS, but also other type of regressions like probit. And the current one that I was working was interval regression. It was the equivalent. The model was like to maximize the likelihood function of some interval parts, and because the survey asks whether you work smaller than 20 hours, between hours and 30 hours, and 30 hours to 40 hours, and 40 hours above, and we are interested in what determines the hour they work we don't observe each individual data. So the model become a bit complex. However, it fits this framework as long as we solve the first order conditions and generate the moment conditions. And adding the second type will also kind of relate the data and give you estimates. Yes.
Well, on behalf of the group, I'd like to thank you very much, Felix, for the interesting presentation, and particularly seeing something for probably many of us, which is fairly complex, applied to something that people are thinking about and we've been talking about actually in our class. So thanks very much.
Thank you. Thank you.